Module 2, Hardware, Environment, and Configuration. Hi, this is Bradley Ball again, and what we're going to do is we're going to talk through your hardware environment configuration, because one of the key things that I find often when I go into places, whether I'm doing a performance tuning engagement or just working on them on their regular systems, the number one thing for performance tuning is to make sure that you've selected the right hardware and that also you've configured your SQL Server environment properly. As long as SQL Server is configured optimally, you should be in pretty good shape. It's from there that we find more intricate things that truly need good performance tuning and diagnosis. And you would be surprised how often we go into an environment, myself or any of my team members here at Pragmatic Works, and we find simple and small misconfiguration items. So our agenda, we're going to cover hardware concepts. We're going to talk about latency, managing trade-offs. We're going to talk about processors and their architecture, hyperthreading, and processor features. We'll discuss memory, the virtual memory manager, page files, and memory limits. We're going to talk about storage, different types of storage, RAID, measuring speed, capacity, and throughput. And then we're going to talk about network basics and some settings that you should look at. So latency. What are we waiting for? When we look at the different things that we wait on in SQL Server, it's generally 4 different resources. You're either waiting for CPU, you're waiting to allocate memory, you're waiting to read something from your disk, or you're waiting for something to be transmitted over the network. We're going to cover this several times throughout this slide deck. And one of the key things that I want to make sure that people understand is what and why we should be looking at this. And part of the reason is that our different components within a server communicate at different levels. So if we take the actual amount of time that it takes us to process something versus the normalized time, this gives us a pretty good scale to be able to say, let's just look and see how these incredibly quick actions normally end up actually taking us a large amount of time. So for example, our average CPU cycle is about 0.3 nanoseconds. Our level 1 cache access is less than 1 nanosecond, and there's 3 levels, level 1, level 2, and level 3. Level 2 is 2.8 nanoseconds. Level 3 is 12.9 nanoseconds. Our main memory access, when we access actual physical data in memory, is 120 nanoseconds. Solid-state disk is about 50 to 150 microseconds. Rotational disk is about 1 to 10 milliseconds. The internet speed from San Francisco to New York City is about 40 milliseconds. Internet speed from San Francisco to the United Kingdom, 81 milliseconds. From San Francisco to Australia, you're looking at about 183 milliseconds. Virtualized operating system reboot is about 4 seconds. A SCSI command timeout is about 30. Hardware virtualization reboot is about 40 seconds, and a physical system reboot is about 5 minutes. Now, if we take all of that and we normalize it, let's make a CPU cycle 1 actual second, we begin to see how these time streams actually matter. Our level 1 cache becomes 3 to 9 to 43 seconds. We're still under a minute, but we're getting close to a minute because it matters what level of cache we're processing within our processor. Our main system memory access takes about 6 minutes. Solid-state disks take about 2 to 6 days. Rotational disks take about 1 to 2 months. Now, as you can see, there's quite a jump here, and that's because of the difference between microseconds and milliseconds. Often when I hear people talk about using solid-state disks, they don't understand that part of the reason that solid states are instantly that much faster is there is a factor of 10 difference between solid-state disk and rotational disks. Your internet access that used to be 40 milliseconds is about 4 years, 8 years, 19 years. And if you think it takes a long time for you to reboot your computer now, when you think of regular seconds in contrast to nanoseconds, operating system virtualized reboot within a container would be 423 years. SCSI command timeout would be 3,000 years. Hardware virtualization reboot would be 4,000 years, and a physical system reboot would take about 32 millennium. And it may already feel like it's taking 32 millennium, but our goal is to be able to make things faster. Where this matters to us as SQL Server DBAs is understanding where we spend the biggest block of our time. And the biggest block of our time will be rotational and solid state to be able to understand why this is so superior. We have to deal with a lot of rotational in our jobs though, so it's also to understand why we're slowing down whenever we have to push something out to physical disk or we're reading from physical disk. Conversely, when you look at our internet speeds here, you can also see why we want our application server and our database server to be within the same data center. Because hops over these long distances just to begin communicating take a lot of time. Not only that, but we want our application and our database server to be co-located within the same data center within as few hops as possible, so we can make sure that communication is as fast as we can possibly have it. This is a balancing act. No easy way around it. We need our CPU, our memory, and our disks to work as one. This is truly one of those things where if we have an issue with one of them, we are only going to move at the speed of our slowest. I may have great CPU, I may have great memory, I may have great disk, but if my network is terrible, I can only communicate with my application server as fast as that network connection allows me to. And each one of these also comes at a penalty. If you need scalability, reliability, performance, that's certainly going to affect the price. And unfortunately, when it comes to IT shops, we don't have unlimited budgets that we're working with. Bottlenecks are bad. I don't know about you, but I would hate to be stuck in traffic like the folks over there on the right-hand side. Good system engineers reduce bottlenecks. They make appropriate design trade-offs where we need to. I'm a realist, and I realize there is only a certain amount of things that we have to work with. What we want to do is we want to make the best physical choices that we can. The main idea is for us to identify where our bottlenecks are and attempt to streamline them. When everything is in tune, you flow like a well-oiled machine. We're starting this out by looking at our CPU. You can see that in this case, our CPU has pretty good throughput. We've got a good I/O channel, but the sequential capability of our storage system is not that great. Our maximum system output is going to be our storage capacity. The next one, our CPU is good, our throughput is throttled. Our IOPS, though, are really good for our storage system. Our max system is throughput capacity constrained. On this next one, we've got CPU limitation, even though our throughput channel and our sequential IOs are a bit better. And in this case, we're maxed out by CPU. The idea is for us to find the right balancing act to be able to get all of our physical resources lined up so we can get the maximum system throughput capacity.